Hello, in this video we're going to go through the mark scheme for the electricity at home exam, which you should have done for homework earlier this week. You're going to need a green pen for additions and corrections and a blue pen to make any annotations. So the coffee machine has a metal case. It's a coffee machine used to heat water. Why is it dangerous for the live wire of the electric cable to touch the metal case? The live wire, remember, is carrying current into the device. It has a potential difference of 230 volts. If that touches the metal case, metal is a conductor. It's a good conductor, so it can also carry a current. What that means is if a person then touches that metal case, which is possible to do because it is the case, that they could complete the circuit and therefore get an electric shock. So what you need to write is there is a risk of an electric shock if somebody touched the case. You could also say electrocution instead of electric shock. Next question. The power output of the coffee machine is 2.53 kilowatts. So that means that P is 2.53 kilowatts. The mains potential difference is 230 volts, so V is 230 volts. Calculate the current in the potential in the coffee machine. So we need to think of a formula with P, V and I in it, and the formula that I can think of there is P equals I times V. So I'm going to write down what I know. P is 2.53 kilowatts, and before I do anything else I want to get this into standard units. So instead of 2.53 kilowatts, I want it in watts. Kilowatts to watts is getting smaller. Kilowatts to watts. And it's 1,000 times smaller. Smaller you need to multiply. Remember we have multiply and divide. And we're multiplying by 1,000. So multiply by 1,000 gives you 2,530 watts. Current we don't know, and potential difference 230 volts. Writing that out in your formula then, on the right hand side, P equals I times V means 2,530 is 230 times I. Rearranging that, this is a tricky bit. If you divide both sides by 230, you get that the current is 2,530 divided by 230, and that gives you on your calculators 11 amps. Question 2. Most electric kettles use the AC, which is alternating current, mains electric supply. Complete the sentence. The AC main supply has a potential difference 230 volts and a frequency of 50 hertz. You need both of those to get your mark. We've now got 3 electric kettles with 3 different power ratings given underneath. 2,500 watts, 1,800 watts and 2.8 kilowatts. It's going to be easy if I change that first into watts too. And remember, to go from kilowatts to watts is getting smaller, so we're going to multiply. Kilo means 1,000, multiply by 1,000 gives 2,800 watts. The student investigated how the power output of kettle affected the time taken to boil a fixed volume of water. The water in all 3 kettles had an initial temperature of 25 degrees. What type of variable was the time? Well, they are changing the power output, they are measuring the time taken, and they are keeping the initial temperature the same. If we use our chimed, they're changing the power, so power must be independent. This is change independent. And they are measuring time, measure dependent. So time must be the dependent. And it says tick, 1 box. So we just put a tick in there. Which kettle will boil in the shortest time? So you just need to give A, B or C, and it will be kettle C. Give a reason for your answer is the next part. The reason is it has the highest power output, or you could say it transfers the most energy per second. 1 mark for saying kettle C, 1 mark for either of those reasons. Turn the page then. We've got a graph which is showing the energy transferred with time. Really important here, the power output is given by the gradient of the graph. So whatever the gradient is here will be your power output. Calculate the power output. That means we need to calculate the gradient because the power is the gradient. Now, to calculate the gradient of a graph, we want to draw as big as we can a triangle on the graph, and the triangle wants to go through one of the corners of the square. So I can see a nice big triangle here from 0, 0 right the way up to 20 seconds, and from 20 seconds there it is 44,000 up. So I've got a triangle here, it's 20 seconds along the bottom, which I'll call the run. So it's run of 20, and the rise up is 44,000. The formula for gradient is rise divided by run. In this case, my rise is 44,000. My run is 20. That means that so this is power. Gradient, filling that into your calculator, is 2,200, and they've been very nice here, and they've given you the units. So it's 2,200 watts. Write down the equation, so it's looking for an equation that links charge flow, Q, current, I, and time, T. Remember this as quit, Q-I-T, Q equals I times T. You could also write charge in words equals current times time. But if you know your symbols, it saves you a lot of time just to write the symbol equation. Calculate the current, which is I, through the kettle when 2,400 coulombs of charge is Q, flows in 250 seconds, time is T. We've got our formula here, Q equals I times T. So starting off, writing down what you know. Q is 2,400 coulombs, I we don't know, but it's going to be in amps, and T is 250 seconds. Q equals I times T, substitute in those values, rearrange again, you need to divide both sides by 250, gives you a final answer of 9.6 amps. Make sure you are using the Michaela layout here so that you are reducing the chance of making a mistake. The next question is about a person who is accidentally touching the live wire inside an electricity socket. Now we are told that the electricity socket is 230 volts, so I'm going to put a big V there so I know my V. And we know that the resistance R is 50 kilo ohms. Now while I'm doing this, I'm just going to do this again and try and write this resistance in ohms. If I go from kilo ohms to ohms, I'm getting smaller, and kilo means 1,000. If I'm getting smaller, I need to multiply. So 50 kilo ohms is going to be 50,000 ohms. Write down the equation that links current I, resistance R, and potential difference V. Hopefully you recognise the I, the R, and the V, and that formula is V equals I times R. You can also write potential difference equals current times resistance. Now we need to do a calculation, calculate the current. So we're going to write down on the left everything that we know. 230 volts. We don't know the current, but we know it's going to be in amps. And the resistance is 50 kilo ohms, which I've just worked out. Multiply by 1,000 to give 50,000 ohms. If you did not convert this correctly, you would lose 1 mark. So you get 2 out of 3 if your final answer is 1,000 times too big. For example, if it's 4.6 amps rather than 0.0046. Substituting your values in to the formula, V equals I times R gives you 230 equals 50,000 times I. Rearranging again, dividing both sides by 50,000 gives you either 0.0046 amps, or if you're using standard form, you might write that as 4.6 times 10 to the minus 3. Either's fine for 3 marks. Rubber is a good insulator. Explain why it's a good idea for electricians to wear rubber-soled boots when working. Rubber-soled boots, rubber is a good insulator, so that's the first thing I'm going to say. Rubber is a good insulator, and therefore it has a high resistance. So if you're wearing rubber-soled boots, you have higher overall resistance compared to if you weren't. Higher resistance, if we remember V equals I times R, if you've got the same potential difference, which in this case is 230 volts, so you've got the fixed potential difference, if your resistance goes up, your current must go down. So, higher resistance causes smaller current, or less current. And this is all in the event of a shock. So higher resistance, less current. So altogether, rubber has a higher overall resistance, therefore smaller current when the shock happens. 2 marks. We've now got a quick graph which is showing the current which causes somebody to not be able to let go against the frequency in hertz. Frequency of the mains electricity supply in the UK, we want the frequency, and that is 50 hertz, same as we said earlier. You do need the unit and the value for the mark, so if you didn't put hertz, 0 marks. Now, from a safety point of view, is this suitable? And there's 2 things we can say here. The first thing is, if we look at the graph at 50 hertz, it's actually the lowest current at which you're not able to let go. So that's not good. We would want to be able to let go at as high a current as possible, because we want to always be able to let go. So you could say no, because 50 hertz has the lowest current for which you're unable to let go. That would be your full mark. However, you could also say yes, and the reason you could say yes is because altogether there's not much difference between these currents. It's between 10 and 12 milliamps. Not much difference. So you could say yes, because the frequency only has a small effect on the current at which the person's unable to let go. So either of those is fine for that mark. Final one is another kettle, and this time we've got an earth wire which is connected to the metal case. Key bit of information there. If there's a fault that makes the metal case live. The earth and the fuse inside the plug protect you from a metal shock. And how do they do that? Well, the earth wire has a low resistance. This means that the current will flow through this should say earth wire. And it will be a high current. A high current will flow through the earth wire because it's a low resistance. And that current will cause the through the live wire to the earth wire. That's what I was writing, sorry. Through the live wire to the earth wire. This current will cause the fuse to melt. That will break the circuit, and that will mean no current flows at all because there's no longer a complete circuit. So 1 mark for saying low resistance on the earth wire. 1 mark if you said the current flows through the live wire or the metal case to the earth wire. That's the important bit. It flows to the earth wire. And maximum of 2 marks, 2 of these, but you would also have a mark for saying the fuse melts, and that will break the circuit. There's no longer a complete circuit and no current will flow at all. We've now got an electrician replacing a shower. Explain why they shouldn't change the shower until they've switched off the mains. And the reason for this is, we've done this on the opposite page. They may receive an electric shock if they touch the wire. 1 mark for those two, each of those points.